Oh my goodness.
Yeah. Okay. So this is 10.1, which is about this thing. I mean, that's what 10.1 is about. It's about the little this thing.
So false rooting.
So the first thing I want you to remember or know is this false rooting thing, which is a little bit like false canceling, right? Do not do this. This is not true. Okay?
Don't do that.
Okay? Do not do this. That said, I guarantee you all of you will do this at some point. Okay? So I'm going to yell at you briefly. It's just like the false cancel. Just don't do it. It's not a big deal. I'm not going to harp at you forever about it. But every time you do it, I am going to yell at you a little bit. Cool? Just a little. Just enough to get you not to do it again. I'd use shock collars, but you're not allowed to experiment on people or zap them. Okay, so anyway, false cancels, right? Okay? Don't do this.
Got it.
Okay, good. All right, that said, again, it is a mistake. It will happen. We'll talk about it when it does. Let's see. We need some definitions for these things. So, do you guys see them with little numbers here?
No. I never. What?
Never seen this?
No. Yes. My calculator has that.
Your calculator has one of these on it, probably. There's like something like this on your calculator.
Oh, that sub stuff again.
What's this about? So what do we mean by this funny symbol? No. So these shouldn't be too bad. First things first, we should just have a way to say it, right? Okay, so let's get a way to say it, so at least we're not stumbling over that. So what we do is we read the and, right? So we say and then what's the little whoopty thing?
Square root.
That's a root symbol, right? Or a square root. It's a square root when n is 2. Otherwise, it's a nth root.
A what? What? Say that again. What happens when it's saying 2 is what?
So squaring is raising to the second power, right?
Oh, okay.
Right? So that's why we call it a square root when it's second root.
Okay.
So otherwise, I'm going to call it an nth root. You guys okay with that? It's just a way to say this symbol. Nth root of x.
Okay. But only if it's not 2.
Yeah, if it's 2, so maybe further. If n is 2, it's a square root. And if n is 3, it's a cube root. The reason for this is actually just to be confusing. Okay, so we made up this notation to confuse you. It's an nth root except for when n is 2 or 3. When n is 2, it's a square root because we call the second power squaring. When n is 3, we call it cube root because we call the third power cubing.
And do we go higher than that as cubing starts?
So, does life go higher than that? Yes. Are we going to often go higher than that? Probably not. We might do fourth roots occasionally.
Okay, when they start doing that, whatever position we will be in, we'll have a computer to plug it in, right?
No.
No.
Some of them are easy. You guys want to see one?
Yes,
My knees and
The
please.
super.
Okay, so let's start super easy.
Okay, like just 5 grams.
Okay,
That's great.
so here's some examples. Can we do this one?
Yeah.
So that's just a regular square.
Yeah, this is just a regular square root, right? So I read this square root or second root, right? Of 4. And this is 2. Okay, we know how to do that. All right, let's see. Let's do the, how about cube root of 8? Do I know that? 2. Why is it 2?
Because 2 times 2.
Yeah, really what I'm thinking here, right, is this is because, right, 2 cubed is 8. So this little thing asks a question, right? What's the question that it asks? In other words, can I define this symbol to mean something?
Oh, the x. Is it like the exponent for the number? That would end up being under the square root.
Okay.
I don't think I'm saying that right.
No, you're actually quite close. So the nth root of x is and then there's a confusing word here, principal, okay, which we're going to get a definition for in a second. This is another thing just to confuse you, right? So it's the principal number with number to the n is x. You guys see that? So over here I'm asking, what's the number you cube to get 8?
Yeah.
2. You guys cool with that? Okay, so how about the cube root of 27?
3.
3. Because 3 times 3 times 3, right? This is 3 cubed is 27. You guys see that?
So it's taking the n of a
Yeah, it's taking n of these guys, right?
So based on the answer, you find the other part.
Mm-hmm.
See,
So
this is
how
why you
about
should start simple.
the 4th root of 16?
Oh, shit. I don't know.
You guys are faster at this than you think, right? You ask, okay, what do I multiply by itself 4 times to get 16? Oh, 2 does that, right?
Oh.
That's 2 because 2 to the 4th is 16. Yeah, sometimes these aren't convenient, right? Just like square roots sometimes aren't convenient. Like the square root of 2 isn't a very convenient number. The 3rd root of 7 is also not a very convenient number. You just can't get you can't get a nice number, so what do? Let's try one. Cube root of 7. Let's see. The cube root of 8 is 2, right? The cube root of 7 is smaller. Is it 1?
No.
Why not? Because 1 times 1 times 1 is 1, which is smaller than 7. Okay, so I know it's between, right? And actually, I know it's not 2 and it's not 1, right? So I know it's between 1 and 2. Can I do any better? Yeah, so if I'm willing to settle for an approximation, what's the cube root of 7? Anybody know how to put that in their calculator?
Somebody said 1.5. Oh.
Okay, so let's see. We grab our TI whatever.
Could you just look at it in the form of like it's say like it's bigger than 2 or bigger than 1 but
Oh my
smaller
god,
than 2?
I have no idea how to use this thing, right? It has like lots of buttons. Let's see, so we might remember that if I take 7 and I raise it to the 1/3 power on the calculator, that I get the cube root. You guys probably don't remember that, right? Okay, so I'm getting out of the calculator, the cube root of 7 is 1.91 and some stuff. What I did in the calculator was I did 7 caret 1 slash 3.
Carrot?
Caret. This thing? Yeah, it's called a caret. This is how you put 7, the cube root of 7 in a calculator. We're going to talk about this some more later, right? But sometimes they're just not convenient. You guys cool with this? So this is the beginning of 10.1. We're going to do some more of 10.1 later.
Jesus, Mary.
All right.
Oh, God.
So 10.1. We talked about this a bit, right?
Scary crack.
No, that was the other chapter. This is
False
rooting.
rooting.
Okay, so we need to remember false rooting. Okay, so what was false rooting?
You can't take x plus y root of x plus y to make it the square root of x plus y.
This business, right?
Yep, that's
The square root does not play nice with addition the way you want it to. Okay, so remember, this box is false. Okay, I'm trying to get you not to write this down too many times. Yeah, the square root does play nice with some things, so we might remember those, right? Really, this is for nth roots too. It's not just square root. But we might remember, right, that there are some nice things about the square root, and really about the nth roots. How does it play with multiplication?
That's nice.
Yeah, this is nice, right? I can break it up the way I think probably it should. So I get the nth root of A times the nth root of B. Okay, cool. What's the other thing that it plays nice with? Okay, so we should remember that the square root doesn't take negative numbers. It doesn't know what to do with them. Okay, that's a domain range thing. We're going to get to that in a minute. How about, oh yeah, it plays nice with division, right? So also, right, so this is true. And if I take the nth root of A over B, that's the nth root of A over the nth root of B.
How do you say that again? The n what?
Nth root of A, right? Remember I say this symbol, n root of A over B is nth root of A over nth root of B. Guys cool with that? Okay. So I might remember these. These are good rules to know. These are the ones that work, right? It's the nth root plays nice with multiplication and division, really because it's an exponent, right? We talked about that at the beginning of the year. Some of you are like, wait, what? Exponent? If you remember what an exponent is, great. We're going to talk about it some more later. Okay. But for right now, just remember these are the ways it plays nice. This is not something it does, so don't do this. Cool? All right. Kind of. Okay. So let's get some graphs. Okay. So really what I want to talk about is I want to think about a function of x that's the square root of x. You guys okay with this? Remember what a function does, right? So this is a rule, right, for taking numbers and turning them into other numbers. There are some questions I could ask, right? Like, what's this stuff? What do I get out? We could try to graph this first. What do you guys want? Do you want to think about these first or try to graph? Think about these? Okay, so let's think about these. You had part of it. So This is the square root, right? It takes some numbers and turns them into other numbers. What are the numbers I can fit into the square root? In other words, what's the domain, right? Remember, here, this guy's the domain, right? This guy's the range. Okay, so what kind of numbers can I fit into the square root function? Positive ones?
And ones that can be multiplied by themselves.
Okay, so positive real numbers, really the ones I can think of as being something multiplied by itself, right? So that gives me positive real numbers. Is 0 in there or not?
I would think that it can be.
Can I take the square root of 0?
What was 0?
What do I square to get 0?
0.
Sure. Oh, wait, I just did it, right? Remember, that's really what this thing does, right? This square root, as an idea, is asking, what number do I square to get x? Right? If that question has an answer, then that number was in my domain. So my domain here is positive, reals, and 0.
Can you do imaginary?
See, this is the problem with talking about imaginary numbers. Yes, you can fit imaginary numbers in. If we think about fitting negative numbers in here, right, then I have to expand my idea of a range. And my range might be to complex numbers. I don't want to deal with complex numbers too much, so I'm going to sort of suppress that. We're going to say we're talking about the square root that gives me positive numbers out, or real numbers out. How about that? Yeah?
Why can't we take a negative number if we have an I?
If you are willing to get an I, you can certainly take a negative number. Yeah. So there are two kinds of square root functions, right? The one we're going to play with in this class is the one that takes positive real numbers and turns them into real numbers, right? There's an alternate version of this function which takes whatever over here and turns it into complex numbers. The reason I don't want to play that game is that complex space is two-dimensional, and I don't want to try to draw a graph that looks like this, right? It's my domain, my square root, and it goes over here, right? Yeah, I can't draw a graph of this nicely, so I'm going to suppress that until we get to a higher class. Cool? Does that make sense? Okay, so no negatives in square roots, even though you know they come out as complex numbers. Cool? What's that?
Like the number 2.
Yeah, so I can't take a square root and get a nice number, right? But it's certainly a number. Does that make sense? Okay, so I've got positive real numbers and 0. How do I write that as an interval? Can I do that? Zero to infinity. Okay, infinity is soft because infinity is not really a number, right? And 0 is hard because I'm including 0. Okay, see that?
Because you're including it or because you're stopping it?
Because I'm including it. Also because I'm stopping there. Right, I'm stopping at 0, but I'm then including that number 0. You guys cool with this? So this is the domain. What kind of numbers can I get out? When I take a square root, yeah, really, I get the same thing.
Don't you get like?
Can I get a negative?
No.
Oh,
No.
not all kinds then.
Yeah, I get all kinds, meaning real numbers, but not negatives, right? Because if I multiply, wait,
A negative and a negative is positive, so always have the positive.
yeah, you guys see that? Okay, so my range is 0 to infinity.
that's as an interval.
Yep, and that's as an interval. Okay, so can I draw a picture of the square root function?
Yes.
Maybe. Maybe is the right answer. Okay, so let's see. I'm thinking here I want to draw a picture of the graph, right? What's a graph? Picture of a function, right? What are the points on the graph?
But it will be all numbers because we don't know what it.
Yeah, points on a graph, right, are an x comma function of x pair, right? So here I'm looking for my points on my graph are going to be a point, and they're going to look like x root x, right? Is this a point on my graph?
It starts at 0.
This way I wrote it, it is, right? But that's not actually a point on my graph. Why?
Because it's not in the positive or negative.
Yeah, because that output on that one would be negative, and I can't get that. You see that? Okay, so I should be looking for x comma root x's. So what numbers do I know about already? Okay, so what if I take this square root as 0? What do I get? Okay, so that's telling me 0, 0 should be on my graph.
Wouldn't it be
So
any
with
number
4 and
within the
2?
right quadrant?
Oh, that's good. So
25
4 and 2.
or 4.
Wait, which way does it go?
Or would you do 2?
Is it 2 and 4 or 4 and 2?
Then how would you do
Is it this way or this way?
Could it be either?
Oh, wait. No, it's 4 is 2.
Wait, when did you get to 4 and 2?
Okay, so I know that the square root of 4 is 2,
Oh.
and then I'm confused about which way it goes, right? But there should be a input, output, right? So this should be the thing I input, and then the thing that I output. So this should look like, these should look like x comma root x, right? So 4 comma root 4 should be on my picture. Root 4 is 2, that's this one. You guys see that? Yeah, what's up, Sean?
So for like the f of x, so would you put 25 equals 5? Or would you do it
I would
5
put-
and 25?
I would put 25 comma 5, right? Because I'm saying what goes in for the x, that's 25, comma, what's the square root of 25?
That's what I
5. You guys see that? So let me put this one on here. So let's go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Let's see. So I go over 4 up
Would it be 16 and 4?
2. Yeah, okay, so you guys are getting the hang. So let's see, we've got 4 and 2 should be on here.
16 and 12.
We decided 25 and 5 should be on here.
1 and 1.
16 and 4.
No longer 25.
9 and
1
3.
and 1.
Very nice, Kristen. 1 and 1.
9 and 3.
And 9 and 3. Okay, so let me see if I can draw some of those. So the ones that are
That's all the
convenient.
numbers?
No.
Oh, you can go in?
Yeah, we can keep going, right?
Okay.
So these are also just the integer points, right?
But I don't get why you got that many.
There's something and it's square root, right? So I know lots of things that have square roots. They're
So
the
the order
squares.
pair, the y is always going to be a square root.
For this guy, yeah. Because I'm
For
trying
y.
to, yeah, I'm trying to make a graph, right? That graph should be x comma f of x pairs. So my-
Every order is here. Like, so 25.
So this is 25 is the input, and then the square root of 25 is the output, right? Which is 5.
I'm going to have to write that down.
All right, so let's see. Graphing. Which of these are convenient for my picture?
1 and 1 and 2 and 4 and 3.
Like this one, and maybe that one, right? But we get an idea. So 1 and 1 is here. Then I put 4 and 2 on there. Then there should be 9 and 3. So I need one more tick, I guess. You guys see this? So then what do I do with the dots?
Connect them with an arrow
Going
to the right.
Okay, connect them.
And put a circle at the zeros, because that's where it's closed, right?
Cool. All right. So here's our graph of the square root function. What do you notice about this thing? You guys notice anything?
It's increasing.
Yeah, it's increasing from 0 onwards, right? But the rate at which it's increasing is getting slower. That's a really cool thing. You just observed something about the second derivative. That's a calculus concept. That's very cool. We really spend a lot of time talking about that. So what else do I notice about this? You guys see anything cool? Try this. Go like this.
My hand up.
Oh, it's
You guys see it?
Charging.
Glenna? It's a half a parabola.
oh, nice.
You guys see that? Why is it a half a parabola?
Because it's the square root.
Because it's the undoing of the squaring, right? Squaring's a parabola. You guys see that? So if I undo squaring, I should really get kind of a sideways parabola. You guys see that? If I was drawing a parabola, these points would all be switched in order, right? Because they'd be whatever comma whatever squared. So if I switch the axes, I should see the parabola. Switching the axes is as easy as cocking my head, right? Really, I should have to cock my head and then stick it through the board, but whatever.
Okay, so this way, up and down is parabolas, sideways would be the square root.
Yep.
Okay.
Yeah, so this is the square root function. You guys want to see another one?
After I retain.
After you retain this. All right, so we should draw the other one. There are lots of nth root functions, right? There's one for n is 2, which is the one we just drew. There's one for n is 3. There's one for n is 4. Here's a thing to make your lives easier. If you take the points off of this, so we put points on here, right? If you kind of erase the points and the tick marks on the axes and just kind of draw this thing. Right? This is really just, I took the scale off my axes. This is nth root for n even. So 2, 4, 6, 8, 10, all of those look like this. Okay? They're flatter, right? The bigger n gets, the flatter this thing gets. Really, it's because the parabola that you get out of bigger powers gets kind of steeper. Okay? But this is kind of a nice picture to have in your head for n is even. Let's get the n is odd one. It's not so bad. Promise. I'm going to start the n is odd one with a graph because I think we'll get really confused if we try to think about domains and ranges first. Let's see. So let's think about the cube root of x. Okay. And when I think about the cube root of x, what's the question I'm asking?
What times what times what equals?
Yeah, exactly. So what number do I cube instead of square, right, to get x? Cool. Very good. So there's a point on our graph. So let me draw my axes again. Hang on. Okay, so what and what?
2 and 8 for 8 too.
Which way does it go?
8 first.
8's the input, right?
And then you get 27 and
Okay.
I'll skip 1 and 1.
Thank you, Christian, for being the keeper of 1 and
3.
1.
25 and 5. Okay?
What?
No.
You want 25 and 5 or no? Wait.
What's 5 times 5 times 5?
25.
Okay.
Think about this all.
How about 0?
0.
Okay, 0, 0 is on there. What else is on there?
16, 4, and 4.
Okay.
So we're just picking numbers.
Could you show where?
I'm really thinking about cubes, right? So I know 0
Okay.
cubed is 0, 1 cubed is 1, 3 cubed is 27. If I had been doing this in a sensible order, right, I would have done 0, 1, 2, 3, 4, 5, but we're a little scatterbrained. That's okay.
Just a little, huh?
So
Because I was in
You want 64th and 1/4.
what's, don't do that. Yes, we could do some fractional things, but they'd be really hard to draw because I'm bad at drawing with a picture anyway. What about -1? What's -1 cubed?
-1.
-1, right?
Yeah.
So -1 actually has a cube root, right? I can say the cube root of -1 is -1. You guys see that? I can put the negatives in these because I know that if I got a negative out of cubing, the thing I put in was negative, right? It doesn't have the ambiguity that the square root does. How about if I put in, let's see, what's the square, or what's the cube root of -8?
-60.
So what's the point that goes with it? -8, -2. Because -2 cubed is -8, right? Okay, so anybody see another one? Yeah, actually I could just go back through the ones I did and slap negative signs on both sides. That tells me that this picture is symmetrical across some kind of a weird double flip. We haven't done flipping yet, but we will.
That's gonna be a parabola.
Ah, so it's not a parabola. I know it's not a parabola because it's got a left half, right? So let's draw it. See, so there's 0, 0 on there. Where's that?
Right in the middle.
Okay, that's the origin. Great. So we've got 0, 0 on here. Then we go over 1, up 1. Okay. Where's my next one?
-1,
Oh, back 1, back down 1, back 1, down 1, right there. Don't get fooled. What isn't this thing? What does it look like right now?
Line.
Looks like a line, but it
It's
isn't,
gonna
right?
go back the other way.
It does.
It's like a snake.
Yeah, actually. It does something kind of funky. So let's see. Where's the next easiest point to graph? 8 and 2 is probably the next easiest thing. So I go 2, 3, 4, 5, 6, 7, 8, and 2. Where's the next one? Yeah, this one? Because that one ain't easy, right?
No.
That one's going to be over around in here-ish. Right? And it's only 1 unit higher. So this thing's pretty flat out there, right? And it gets flatter, actually. If I do the other -1, so let's see, -8, so -1, -2, -3, -4, -5, -6, -7, -8, and down 2. So I get this kind of,
You're gonna
Yeah, like a
Flat-ass.
snaky whoopty thing. Yeah, like a big flat ass. For snake. Cubic, for cubic. Okay.
So cubing makes a flat snake.
Yeah, so if I asked, okay, this is the cube root function, right? This is this guy that I'm drawing here, the cube root of x. If I was to ask, what's the cubing function look like? So we probably haven't even drawn this one. Maybe if I ask, what's g of x's x cubed look like? It'll be a snake, but it won't be this one, right?
And go the other way.
It'll go kind of the other way somehow, right? Remember I had to kind of cock my head at the other one? Goes like this. You guys want to know a trick for these? If you have a rule and a rule that undoes it, right? A function and a function that undoes the previous, their graphs are flipped across the line y equals x. You guys see that? If I drew the line y equals x in here, and then I take this picture and flip it, I'll get that one. Yeah, because cubing and cube rooting undo each other, right? This is a very subtle thing. We haven't really talked about inverse functions, which is really this conversation. But there is a cool way to get the graphs, and you can just take the function that's kind of the one you're maybe more used to, right? The one that cubes. And if you want to make the cube root function, you flip over y equals x. Cool? All the odd powers look roughly like this. Cool? In the same way that all the even powers look roughly like the square root. Cool? Questions?
Could you write that ordered pair like in x, way?
Yeah. So these ordered pairs are x comma cube root of x.
When you're saying odd and even, you throw me off. What do you mean?
So I mean that if I erase the tick marks off of this thing,
Yeah.
right, it'll look kind of like this. That's a bad picture. There's some weirdness going on in here in the middle that I haven't quite captured with this. But this is the nth root of x, for n is 3, 5, 7, 9.
Oh, okay.
Right, all the odd roots look like this. Cool? You guys want a take-home quiz? Because I don't have a quiz to give you.
Not really. No, you just let us pass.